I'll try to be efficient in my presentation. Okay, so I'm from Loughborough University, as Nash mentioned. Loughborough is 120 miles north of London, for those of you who don't know exactly where it is. So this is part of a big 5 billion euros EU project called Design for Energy. We are 17 partners in this project. The co-authors are down here. The first four authors are from first 5 authors from Loughborough. The other 2 are from Fraunhofer. So what I'm going to do, I'm going to give a quick overview on what design energy is about, what's the main concept and approach. I'm going to move a bit further than what's in the paper because our research moved after we submitted the paper. So I'll show the final product, and then in the form of a flashback, I'm going to focus on the why are we having specific emphasis on retrofitting during operation and maintenance, and how do we link BIM to BEM? Well, all of you know BIM. BEM is Building Energy Modeling. What decision-making approach we are going to use to choose the best retrofitting energy-efficient option, and what are the key performance indicators we are using. So basically, in a nutshell, what Design for Energy is trying to do is to provide architects with tools which help them take early, sensible and correct early design decisions. The problem is that, or the main problem we are facing is that architects are very good in the design, but they don't necessarily, or they are not very professional in making the best energy-related decisions. They may try to base it on some experience or some historical projects, but they are not the experts there. So what we are trying to do is to provide them with tools which help them making the correct design decision at early stage for retrofitting and for early design. We're focusing today on retrofitting and taking in consideration not only the building but the neighborhood. So the same building could be designed differently if it is in different neighborhoods. So the platform which we are about to finalize consists of 3 main pillars here. There is one which gives the designers and the users the processes and the methodologies which they should be adapted at certain instances. So we developed a process model for the design stage, and we developed visionary scenarios. How does the architect perform the design from the very early concept design till detailed design and then operation and maintenance. In the middle block, it's the cloud-based collaboration platform. It has sets of tools there which we developed during the project. So we're having a decision support tool, which I'm going to talk about maybe in more detail. We're having an energy efficient component-based design. We have an energy enhanced. We're having the energy enhanced BIM. So we are complementing the BIM model of the building with energy parameters. We are having neighborhood parameters as well, and we are having tools which would be provide the energy matching facility for the design. So we would indicate what sort of energy levels we want to match, and the design will pick the best possible options, taking into consideration certain rankings. At the top part, we are having the holistic design part of it, where we are looking at the neighborhood parameters as well, and also looking at optimization of the different factors which the user will be choosing. So the user can choose, they want to optimize the design based on, let's say, thermal comfort, or based on cost, or based on return on investment. So there are different parameters there. So how does this platform look and feel? This is how it looks on the web. It's a very simple part about the project which you are starting to design or doing, a part about the team who is working on it, and there is also the part here is about the collaborative tools, so the tools which have been developed, and also we have an information part about the processes which need to be followed. So the logic of the platform, it just follows the logic of the life cycle of a project. So it starts from needs identification, passing by concept design, detailed design, until operation and maintenance. So I'm going to give a snapshot of a couple of stages in the platform. So the first one, which is the needs identification, that's the very early stage. So if you look at the neighborhood parameters there, so you have to input first information about the project, what target values you want to target in terms of energy. You collect information from the neighborhood, could be from city councils or from other sources. You look also at what's the natural environment, the soil, the weather. You look also at the building data of the current neighborhood. We're talking here about in case of retrofit, if you are going to retrofit a neighborhood, you are looking at the building performance information. You are also looking here at the demographic data is important because the same building you can be designing in a neighborhood will be different according to the number, the people, the type of occupants. There is also a knowledge base which is linked in the platform, which has components. So the components here will be called according to the design requirements. So there is a component database where the certain components are imported according to the design parameters. So you have all the information about the neighborhood, and you can filter the information in any way you want. So for example, you can say buildings, if you want to filter buildings with energy rating A or B or C, you can choose the you can choose the top part here. You can choose, for example, buildings or buildings rated A. It will filter this out from the neighborhood information. It will give you all sorts of analysis. This part is the target setting. So this is a tool which was developed as well to set the targets, the energy targets which you want to achieve. So you can play with that and see what sort of impact will the target, when you change the targets, will impact the design. And then you have here all sorts also of neighborhood analysis. You need to have benchmarking data, and this benchmarking data are linked from a database which brings information from all different benchmarks values, like from CIPZ or from any other national sources. And you try always to compare the output from the targets you are setting with the benchmarking data. At the concept design stage, when you after you identify the neighborhood information, you start doing what we call component-based design. So based on the BIM model, you have a space model. We started by using IFC at the beginning, importing of the BIM in IFC, but we had problems with that. So we started using GBXML, and it worked very well. The output of the BIM, we use the conversion tool to input into energy simulation using Energy Plus. The input to format of Energy Plus is IDF, for those of you who use Energy Plus. So we needed to have a conversion from GBXML to have a direct automatic input from GBXML into IDF in order to perform the energy simulation. Once we've done that, the simulation runs and creates different design options which are matched with the energy performance. They are matched with the target setting. So there is another tool which calculates the KPIs which are identified. I'll talk about the KPIs later. And then you end up with a series of options for the design. So these are different design options here. And the ruler on the left hand side is for a KPI. So you can, if you slide this ruler, it will change the level of the KPI, and the design options will change automatically. So it gives you the possibility of trying doing like what if scenarios. So you end up with having automatic update for the BIM and having different design options. While you do that, you have the possibility also of looking at another tool which we've done, which is Energy Metric Options Analyzer. So for each option you do, you compare it with the target which you set and try to see how close are you from the energy which are matching. I'll skip the other stages because we don't have time. I'll talk about the operation and maintenance stage, where we have here, we get the information from the building, from the operation stage to wireless sensor network. So we collect operational data and also collect building performance data. We link that with the information from the BIM, and we start to do some analysis on the current performance of the building. And using links with a database, a component catalog database, we set the target for the energy which we want to match, and we start exploring what components we need to use. So, for example, we can try changing the windows. We can try changing the let's say the insulation. We can try using renewables like photovoltaic. So each time there is a query with the database imports the components, and the design is done or redone. And every time the energy performance goes through the energy simulation, and you come up at the end with several options, and the options will be ranked according to what the user wants to prioritize. So the priority could be, for example, the return on investment. The priority could be the thermal comfort, the energy efficiency, etc. So why do we focus on, or why are we giving some emphasis on retrofitting? Well, one of the problems is that there are challenges with existing buildings that, as we all know, for all buildings which need retrofitting, BIM does not necessarily exist. So we need to determine what are the minimum data requirements for a BIM model to be used for retrofitting. And also the other problem with the current practice is that usually designers use default data, not operational data, and this can result in problems that it can be very far away from the operational data. So what should be used is measured operational data using tools like wireless sensor networks, for example. So this is again to emphasize the importance of the retrofitting, that, for example, substantial share of the stock is older than 50 years, etc. So this is just part of the literature which was done. So this shows why the future research should be focusing on retrofitting. Another problem which emphasizes the limitations in the current practice is that when we are looking at BIM model of buildings in the current state, and then we take the BIM model and try to use, for example, OpenStudio or Design Builder in order to input the data in Energy Plus. What happens is that the Energy Plus will produce predicted energy performance, and based on that, you can have some retrofitting measures. However, the problem, as I mentioned, so you can do all your decision making based on the default values which you input in Energy Plus. But what should happen? There should be a transparent conversion process during the design for retrofitting, where you should enable comparison with measurements, not just using default values. So this emphasizes the problem that the retrofit decision making, for example, is not supported by data because it does not use the operational data. This just quickly in a minute or so shows the workflow which we are using. So in the retrofitting scenario, what we do, we conduct, or usually a facility manager will conduct a survey for the current state of the building and see if there is a good energy performance or not. If there's good energy performance, yes, then you don't need to do anything. But now, if the energy performance is not as we want it to be, then we'll look into building a BIM model, a Revit model, and then we extract the data from in GBXML. What we found that current Revit models, architects do not build them in a way which allows you to extract the correct GBXML. So one of the things we've done, we developed a good GBXML guide for architects to produce models to be able to convert into GBXML. So produce good GBXML, export guidelines for Revit, and then this GBXML file, you are allowed to edit it with any components, for example. And then another problem which we need to handle is how we convert the output of Revit into Energy Plus, which is from GBXML into IDF. So we developed also a conversion tool which automatically converts GBXML into IDF. Then the third tool which we've done we take the data from the IDF, we run Energy Plus, and the output from Energy Plus, we calculate the KPIs. The KPIs, so there's another tool which we have, which is called Energy Plus KPI tool. So you calculate the KPIs which related to comfort, to energy efficiency, to cost, to return on investment. And this at the end will help you generate some alternatives. So the alternatives are generated using what we call options generator, and the options generator will produce some options which will be ranked based on input from the user, on what basis the options you want them to be ranked. So they could be ranked based on cost, on energy, on return on investment, on any parameter. They could be ranked and weighted, and then you will have at the end different options or different ranked alternatives where the architect can make a decision on what to choose. I'm not going to talk much about that. This is the architecture of the option generator. Just a quick idea about what we used in terms of decision support. We use the multi-criteria decision making, the algorithms, we use them there for generating the options. I think most of you know it already. There are different ways of applying multi-criteria decision making. We use TOPSIS method here. You can read about more about TOPSIS in the paper, but this shows the background of the algorithms which we used in order to take the decisions. Again, these are just some mathematical formula. Maybe the last thing worth mentioning, the KPIs which we use. We use different sources for KPIs. So, for example, our partners VTT, they had some KPIs which they use, like net present value. The slight difference between the KPIs which are mentioned here, that because the tool, we used it for new build and for retrofitting. So, for example, in new build, you will look more into net present value, while in retrofit, you look on return on investment in sense if you are going to buy new windows, do double glazing or triple glazing, or do renewables. So they're slightly different, but they are very much related. So I consider also in terms of KPIs, air quality, thermal comfort, carbon footprint. So these are the sets of KPIs where Energy Plus every time runs the calculation, and then the decision is made on best alternative. So at the end, what we get first a run for the base case which we have, and then we have different runs for the different options. And every time, so for example, this is the case of the thermal comfort. So it gives you different design values here for different alternatives. So you have here different alternatives here. Also, for example, here also you have different alternatives. So for when you're considering thermal comfort, you will look at alternative one of some sort of insulation, superficial 34, or you can have another type of insulation here, or maybe you can use photovoltaics, and you have some analysis of the alternatives which will help making a decision. So what do we conclude from this? That there is really a need for such tools. There is a lack of tools which have architects in their design. We should take in consideration the interaction with different neighborhood components. So not only the building as such as standalone, but also how it interacts with the neighborhood. There is also a need for linking BIM with building energy modeling. This is an area which is lacking right now. There's lots of research in this area, but this needs to be emphasized. Also, you need to take in consideration different KPIs and try to see mix and match and prioritize which ones you find more important than others from your point of view or from the client's point of view. And also the collaborative design platform is needed for the integration of energy, environment, and societal systems. So we are taking into consideration here demographics information, for example, the and other aspects in the neighborhood, in order to improve the energy efficiency within the whole neighborhood. So I tried maybe quickly to just to show what we are doing in Stanford Energy. This is an acknowledgement for the project. As I said, it's a 5 million euros project, which will finish later this year. Thank you very much for listening. Thank you.